cs407 Numerical Analysis, Section 5.3, Gaussian Quadrature Formulas. So you'll remember last time I promised you some nasty fractions and nasty numbers. Well, here they are in this section. So we'll start with a description of what this process is, and we'll end up seeing the derivation as to why we derive these nasty numbers. So most numerical integration formulas conform to the following pattern that you can see in bullet 1 there. The integral from a to b of f of x dx is approximately a sub 0 f of x0 plus a1 f of x1 all the way out to a sub n f of xn. To use these formulas we need a couple things. One thing that we need are the nodes where the evaluation of the function takes place, and the weights that are given to each one of those function evaluations. Those are the capital A sub zeros. Now, there are nice tables that list these numerical values and the weights, and we're going to take a look at those, but first we'll see how those tables get made. So, where do these formulas come from? Well, to tell you the truth, they come from the Math Factory. Now, it's located near Nike's factory in Bandung, Indonesia, and they use kind of cheap labor to derive these. Actually, in all seriousness, one major source of these formulas is the polynomial interpolation techniques used, such as the Legendre interpolation formula that we saw back in chapter 4. In Legendre interpolation, p sub n of x is equal to the sum I equals 0 to n of L sub I of x times f of x sub I, where Li is given by the formula in the second sub-bullet. The Lagrange interpolation provides a polynomial p of degree at most n that interpolates f at the nodes. If circumstances are going to be favorable, then p will be a good approximation of f. So what we can do is we can obtain the following formula for the integration. And again, you'll note that this is an approximate formula. From the way in which this formula is derived, we know that it gives correct values for the integral of every polynomial of at least degree n. Now that we know where they come from, let's take a look at an example of how we can actually use these. So, let's take a look at how we would determine the quadrature formula of the form 1 when the interval is from -2 to 2, and the nodes are -1, 0, and 1. Okay, so here we use the Lagrange interpolation, and derive L sub 0 is 1/2 times x minus 1. L1 is minus x plus 1 times x minus 1. L2 is 1/2 x times x plus 1. We can then go about obtaining the weights, and we get weights of A0 is 8/3, A1 is -4/3, and A2 is 8/3. So we put these all together in the A sub I f of x sub I formula, and we get the following secret recipe. The integral from -2 to 2 of f of x dx is approximately 8/3 f evaluated at -1, -4/3 f evaluated at 0, plus 8/3 f evaluated at 1. As a check of this work, we can verify that the formula gives exact values for the three monomials, that is 1, x, and x squared. By linear algebra, the formula provides correct values for any quadratic polynomial, because we can combine those into a linear form. Now, Gaussian rules for numerical integration are usually given on an interval from 0 to 1 or from -1 to 1. Often we want to use them on a different interval because we integrate over different intervals. We can derive a formula for any other interval by making a linear change in the variables. If the first formula is exact for polynomials of a certain degree, then the same is going to be true for the second that we get from the change of variables. Let's see how this is accomplished. Suppose the numerical integration formula is given from c to d of f of t dt, and we can approximate that using the coefficients a sub I and the function evaluated at points t sub I. If a formula is needed for some other interval, ab, what we can do is we can define a linear function lambda of t such that it traverses cd, and then lambda of t will traverse AB. We change x to lambda of t and dx to lambda prime of t, and that will produce the quadrature rule over AB. In the preceding discussion, the nodes were arbitrary, although for practical reasons they should belong to the interval in which the integration is carried out. It's an important point. Gauss discovered that by a special placement of these nodes, and we'll see the nodes Gauss discovered, the accuracy of the numerical integration process can be greatly increased. This result is captured in the Gaussian Quadrature theorem. This theorem says, let Q be a non-trivial polynomial of degree n plus 1, such that the integral from a to b, x raised to the k, q of x dx, is equal to 0, and x1, x2, all the way out to xn are the zeros of q. Then the formula with these x sub i's as nodes will be exact for all polynomials of degree at most 2n plus 1. And the integral from a to b f of x dx can be approximated by the sum of the a sub I coefficients multiplied by f evaluated at the points x sub I. Now the a sub i's are given by the integral from a to b of the Legendre interpolation of x dx, and that's formula 6. Furthermore, the nodes are going to lie in the open interval AB, again, because that's where we're integrating over. So, as a summary, with arbitrary nodes, the formula will be exact for all polynomials of degree n. With the Gaussian nodes, the ones that Gauss discovered, the formula will be exact for all polynomials of degree 2 times n plus 1. So, if you're using the Gaussian nodes, you can increase the degree of the polynomial. The quadrature formulas that arise as applications of this theorem are called the Gaussian or Gauss-Legendre quadrature formulas. There's a different formula for each interval AB and each value of n. Let's derive a Gaussian formula that's not very complicated. This is example 2. We want to determine the Gaussian quadrature formula with 3 Gaussian nodes and 3 weights for the interval minus 1 to 1 f of x dx. Well, the first step here is to find q of x that's referred to in the theorem and compute its roots. So q of x is going to have the form c sub 0 plus c1x plus c2x squared plus c3x cubed, and should satisfy the following conditions. The integral from minus 1 to 1 of q of x is equal to the integral from minus 1 to 1 of x q of x, which is equal to the integral from minus 1 to 1 of x squared q of x. So let's let c0 equals c2 equals 0. Then q of x is given by c1x plus c3x cubed. And what we can obtain is the integral from minus 1 to 1 of q of x is equal to the integral from minus 1 to 1 of x squared dx, and that's 0. And that's since the integral of an odd function over a symmetric interval is 0. To obtain c1 and c3, we impose the condition the integral from minus 1 to 1 xc1 of x, or xc1 times x plus c3 times x cubed dx equals 0, and we solve for c1 equals minus 3, or solve, and we get c1 is equal to minus 3, and c3 is equal to 5. So q of x becomes 5x cubed minus 3x, and we can derive those roots with a little bit of algebra, and these are indeed the Gaussian nodes that you're looking for. So move along. I know the Jedi mind tricks only work on the weak-minded, but we really don't want to do all that algebra. So I'm going to move it along. Now what we need to do is obtain the weight notes for A0, A1, and A2. To determine these weight nodes, what we do is we use the procedure known as the method of undetermined coefficients. We want to select A0, A1, and A2 in the formula below this formula here, so that the approximate equality right here is an exact equality whenever f is of the form ax squared plus bx plus c. Now, since integration is a linear process, the result will be exact for all polynomials of degree less than 2 if it's exact for the monomials 1, x, and x squared. Now what we can do is we can arrange these calculations in tabular form. And we put them into a table, and what you'll notice is we have the left-hand side, which are integrations of the monomials, And the evaluation of those, 2, 0, and 2/3. And we have the right-hand side, which are systems of linear equations. So, what we end up having is a system of 3 linear equations and 3 unknowns. And we can solve this to get A0 is equal to A2, which is 5/9, and A1 is 8/9. And that will allow us to produce a formula to approximate the integration on the interval -1 to 1 of f of x. And again, you can see that we have the weights and we have the nodes. So we're going to use the 3 nodes that we discovered in the last slide minus square root of 3/5, 0, and the square root of 3/5. And the weights that we discovered by solving this system of linear equations. This is going to integrate correctly all polynomials up to and including the quintic ones, so degree 5, because they're taking place at Gaussian nodes, so we can go up to 2n plus 1 accuracy. We can also apply a transformation to use the integral over any other interval that we like. So, in other words, these rules can transform in the same way that a Super Saiyan can transform. Here we let t equal 2x minus b plus a divided by the quantity b minus a. And then a Gaussian quadrature rule of the form from -1 to 1 f of t dt is approximately equal to the sum from I equals 0 to n of the weights times the function evaluated at the nodes. And then it can be used over the general interval a to b, given this formula, which is 1/2 b minus a times the integral, again we normalize to -1, 1, of f evaluated at 1/2 b minus at plus 1/2 b plus a dt. So, we can look at how we can use this result in the previous one in an evaluation. So, here we have our nasty equation e to the minus x squared, the one that's related to the error function. Now, it's going from 0 to 1, and we have those formulas for -1 to 1. So, what we want to do is first we start with what is a. A is 0, the lower bound on the integral, and b is 1, the upper bound. So, the integral from 0 to 1 f of x dx is equal to 1/2 times the integral from -1 to 1 f evaluated at 1/2 t plus 1/2 dt. And we can basically take out our handy calculator after we get the result down here. And again, f is e to the minus x squared. Take out our handy calculator, and we get a result of 0.74681. And that compares against the true solution, which is 1/2 the square root of pi times the error function evaluated at 1, 0.74682. And the error in the computed solution is approximately 10 to the minus 5, which is excellent considering that we only did 3 function evaluations. They were nasty, but there were only 3 of them. And when you put it into a computer, you won't even notice the nastiness. So the Legendre polynomials help us by providing an efficient method for generating special polynomials whose roots are used in the quadrature formulas. So if we specialize the integral from -1 to 1 of f of x dx and standardize q sub n so that q sub n of 1 is equal to 1, then we get a special type of polynomial called the Legendre polynomials. And the roots of these Legendre polynomials actually turn out to be the nodes that we use for Gaussian quadrature on -1 to 1. The first few Legendre polynomials are q0 of x equals 1, q1 of x is equal to x, q2 of x is equal to 3/2 x squared minus 1/2, and q3 is 5/2 x cubed minus 3/2. We can generate them through a 3-term recurrence relation, and so putting this into a computer or doing the recurrence relation shouldn't give you much problems at this point, and you can derive higher order Legendre polynomials. Now what we can do is we can treat integrals of the form, the integral from a to b f of x times w of x dx, where w of x is a fixed positive function on AB, for which the integral from a to b x to the n wx dx all exist. And some important examples for this interval, for the interval minus 1 to 1 for w of x, are w of x is equal to 1 minus x squared raised to the 1/2, so the square root of 1 minus x squared, and then the 1 over the square root of 1 minus x squared, and the square root of 1 minus x squared. This leads us to the Gaussian Quadrature theorem. And again, this is basically constructive as to how to go about deriving these Gaussian quadrature nodes. This is the theorem, and it's something that you'll just have to memorize for the test. The good news is that you don't have to memorize it for the test, and also that you can use this previously developed theory to get the nodes and weights for different values of n in the quadrature formula. The integral from minus 1 to 1 f of x dx is approximated by the sum of the weights a sub I times the function evaluated nodes. In fact, the numerical values of the nodes and weights for various values of n up to 95 can be found in the Abramowitz and Stiegen book that's mentioned several times in this text, and I've included a link to that text. It's actually online now. By the way, when you search in Bing, it brings up a picture of a beer as the second image for this search. It also suggested car parts and accessories. Anyway, let's look at some of the ugliness that results from these. Yeah, I think we don't have to go up to 95. In fact, this should probably be enough to let you know that these are not the prettiest of numbers, but again, when you put them in the computer, it doesn't matter. The table on 245 goes all the way up to n equals 4. I've only shown up to n equals 3 here. Since these nodes and weights are mostly irrational numbers, they're not good for hand computation, obviously. And we saw some simpler rules back in section 5.3 that involved integer and rational values. However, in programs for automatic computation, it doesn't matter whether it looks elegant, and the Gaussian quadrature formulas usually give greater accuracy with fewer function evaluations, which is what we're looking for in a computer program. The choice of quadrature formulas depends on the specific application being developed, and in order to determine which ones to use, you should probably take a look at that Stiegen and Abramowitz book if you're going to do something more advanced than what we're covering here. Last but not least, the singularity is indeed near, but you can remove it. Basically, if either the interval of integration is unbounded or the function of integration is unbounded, then you need to use special procedures to obtain accurate approximations of these integrals. And one approach for handling a singularity where the function becomes unbounded or is undefined is to change the variables to remove the singularity and then use the standard approximation technique. Important case where Gaussian formulas have an advantage occurs in integrating a function that is infinite at one end of the interval. And that's because the Gaussian nodes are always interior points of the interval. So, next time, spline functions.